Today we're going to talk about the problem of establishing trigonometric identities. Now, there's a bunch of standard identities for trig functions, and those are just identities that you need to remember, basically, although you can usually prove them from first principles if you want to. But once we have those basic identities, then there's going to be some other identities that you can establish and use them, basically, to simplify various expressions with trig functions, and then use this method of simplifying the expressions to prove new identities using or new identities that involve the trig functions. So I want to start by reminding you of a few of the identities that are sort of basic standard identities that you just need to remember. So some of these are just the definitions of the trig functions. For example, the tangent of theta is equal to the sine of theta divided by the cosine of theta, and the cotangent of theta is the cosine of theta divided by sine of theta. These are not really things that you prove because these are just the definitions of these functions. So these are pretty standard. Now, there's a few other identities that you want to remember. And excuse me for a moment while I find the page of the book. Right. It's page 636 that lists these identities. I may as well write them out here for you anyway, because they're pretty short. The other two trig functions, cosecant theta, this is 1 over sine theta, and secant of theta is 1 over cosine theta. Remember, the trick for keeping track of which one of these is which is that the co gets flipped. So cosecant goes with regular sine. Secant goes with cosine. So the co flips. And the function flips as well. We flip to the reciprocal. So these are just kind of the definitional identities of what are these four trig functions. There's nothing particularly weird going on there. Next identity that you always want to keep in mind is the Pythagorean identity. So sine squared theta plus cosine squared theta is equal to 1. But there's actually two more forms of the Pythagorean identity that are important to keep in mind. And you get those forms. I had my eraser here like literally 2 seconds ago. There it is. Even here, I managed to lose my eraser on a regular basis. So there's two more forms of the Pythagorean identity, and you get them by dividing both sides of the equation by sine squared or by cosine squared. So let's try doing that and see what we get. If I take sine squared theta plus cosine squared theta equals 1, what would happen if I divided both sides of this equation by sine squared? Well, dividing the left by sine squared, I'm just going to divide everything by sine squared there. On the right-hand side, I'm going to divide everything by sine squared theta as well. There's only one thing on the right, so I just divide that. Now, what's going to happen here? Well, sine squared theta over sine squared theta, this is going to cancel to give me 1. What is cosine squared theta over sine squared theta? Well, this is like cosine divided by sine, then squared. So this is actually cotangent squared theta. And what is the reciprocal of the sine function? Well, we just actually said that. It's one of the things I just erased, right? So when you take the reciprocal of sine, you get cosecant. So this becomes cosecant squared theta. So you get 1 plus cotangent squared theta is equal to cosecant squared theta. This is another form of the Pythagorean identity. So usually when you think about the Pythagorean theorem or the Pythagorean identity, you think about this form involving sine squared and cosine squared. But this is actually a second form of the Pythagorean identity, and it's useful enough in its own right that we think of this, as a separate identity. Although, to be honest, you can get it pretty quickly as you just saw, from the usual way of thinking about the Pythagorean identity in terms of sines and cosines. Now, I said we can do the same trick by dividing everything through here by cosine squared instead. So, what would happen if I start with the regular Pythagorean identity, sine squared theta plus cosine squared theta equals 1? What would happen if I divided everything through by cosine squared theta? I would get a similar identity to the one that we just found. It wouldn't be the same identity, but it would look a little bit similar to it. So I want to encourage you guys, pause the video here and see if you can work out what happens if you divide everything through here by cosine squared theta. Assuming that I can actually write what I'm trying to write here. Okay, were you able to figure it out? If you did it correctly, you would get something that looks almost identical to this expression here, except instead of cotangent and cosecant, it would involve tangent and secant. Because what's going to happen here? Sine squared over cosine squared is actually tangent squared theta. Cosine squared and cosine squared are going to cancel out and give me 1. And the reciprocal of cosine is regular secant. So we get secant squared theta. So tan squared theta plus 1 is equal to secant squared theta. Okay, this is a third form of the Pythagorean identity. So we can think of this as sort of the second form, and this as the third form, if you want to, of the Pythagorean identity. If you are trying to memorize these things, one thing to remember is that in the second and third form, they're really almost the same. The second form involves cotangent and cosecant. The third form involves tangent and secant. So otherwise, these are basically the same thing, because I could rewrite this as 1 plus tan squared theta equals secant squared theta, and now they really look very similar, except that one of them is the regular tangent and secant, one of them is the cotangent and cosecant. So there we have 3 different forms of the Pythagorean identity. And then we have the even and odd identities, the behavior of the various trigonometric functions under the even and odd symmetries. So we know that the cosine of minus theta is equal to cosine theta. And for that reason, we also know that secant of minus theta is equal to secant theta. Then we have sine of negative theta is equal to negative sine theta. And looking at the reciprocal of both sides of this equation, I get that cosecant negative theta is equal to negative cosecant theta. So remember, this means that the cosine is even and the sine is odd. That also means secant is even and cosecant is odd. And then we get relationships for tangent and cotangent. So the tangent of negative theta is equal to negative tan theta, and the cotangent of negative theta is equal to negative cotangent theta. So tangent and cotangent are odd as well. The only even trig functions are cosine and secant. The other 4 are odd functions. Now, what is the point of this kind of stuff? Well, the point of all this stuff is to use these things to simplify expressions that involve trig functions. So basically, if I wanted to, let's just take a quick look here at some examples of this stuff. Now, I'm going to do a bunch of examples here, but this is one of those things where you kind of have to practice it yourself, because each one of these problems, it's a little bit of, there's no formula to use, right? There are some tricks, and we're going to talk about those tricks, but essentially each problem, you just have to kind of look at what's in that problem. What can we do in this particular case to try to simplify it and go from there? So let's think about what would happen if I wanted to simplify an expression like cosecant theta times cosine theta. Well, the way that I could do this, there are a lot of different ways of approaching these kinds of simplification problems. And for that reason, there's not just one simple, this is always the way you want to do it kind of procedure that I can show you. But one thing that I find rather helpful is to think about this sort of thing by rewriting things in terms of sines and cosines. If you can't see anything else to do, rewrite this in terms of sines and cosines. So I can rewrite this and I can say, well, this is the same thing as 1 over sine theta times cosine theta. That's the same thing as cosine theta divided by sine theta. And that is the same as cotangent theta. So what we've done here is we have simplified something that involved two trig functions multiplied together. We've simplified it down to a single trig function. Let's take a look at another example of doing this kind of simplification. So let's see if we can simplify. What's a good example here? Let's suppose that we want to simplify sine of theta times cotangent theta plus tangent theta. So this is a little bit of a longer one in some ways. And again, I do apologize. I keep stepping back and forth, but I'm trying to actually do some problems that are coming out of the book in the book exercises. And so I have to keep grabbing the book from over here. So let's suppose that I want to simplify this. Basically, I want to take something that involves a lot of complicated operations with trig functions. I want to rewrite it in terms of the simplest possible collection of trig functions that I can. Well, the way that I would do this is I would say, okay, let's actually, again, there's a few different ways of doing this, but one way of doing it would be to kind of rewrite things here in terms of sines and cosines. So I can rewrite this as sine theta times, now cotangent is cosine theta divided by sine theta, and tangent is sine theta divided by cosine theta. So let's see what we can do here to simplify this at this point. If I multiply through here, this becomes cosine theta plus sine squared theta divided by cosine theta. Okay, so all I've done here is I distributed the sine theta through these parentheses. The sine theta cancels in the first term. In the second term, I have sine theta times sine theta. That picks up a sine squared. And then we have the cosine theta in the denominator still, of course. Okay. So now what can we do? Well, the thing that we can do is we can take a common denominator here. So let's try doing that. If I take a common denominator, I have to multiply the left-hand term here. I have to multiply this by cosine theta over cosine theta. Remember, I can think of this as a fraction over 1. So this is a denominator of 1. If I multiply by cosine theta over cosine theta, then I have cosine theta over cosine theta times cosine theta over 1 plus sine squared theta divided by cosine theta. Okay, so at this point, this is going to become cosine squared theta over cosine theta plus sine squared theta over cosine theta. And at this point, we ask ourselves why I can't keep track of an eraser. There we go. At this point, I'm going to have to go back to the top of the board, unfortunately, because I don't have a lot of room here. If I put these two fractions together, I'm going to have cos squared theta plus sine squared theta, all divided by cosine theta. So this expression down here is equal to this expression up here. Hopefully everybody can follow, even though I'm sort of moving back to the top of the board here. Now, at this point, we notice cosine squared theta plus sine squared theta, that is one of the Pythagorean identities, and that simplifies to 1. So this is going to become 1 over cosine theta. Now stop for a minute, because whenever you see a reciprocal of a trig function like this by itself, you know that that can turn into another trig function. We know that there are these reciprocal identities that really just come from the definitions. So what is the reciprocal of 1 over cosine theta? Do you remember? So the co flips, and this is going to become secant theta. So we have now started off with this expression, which is a rather big and kind of, I mean, it's not too horrible, but it's not a very simple expression. I mean, what does this look like? If I asked you, hey, graph this expression for me, it'd be very difficult to do. I mean, I don't know how I would just graph this thing off the top of my head, okay? I'm not going to be able to figure that out very well. But after we've done some simplification, we find, oh, hey, this is actually just secant theta. That's all it is. And we know how to graph secant theta. We've looked at that before. So if you wanted to graph this thing, then after the simplification, you'd be done. I want to pause here for one moment and make an observation, okay? Because I do want to say, when you're establishing these identities, there is a tendency to kind of gloss over the fact that sometimes the cancellations that we make, there will be certain points where they don't work, okay? So for example, when I said sine theta times cosine theta over sine theta, oh, that cancels to give me cosine theta. Well, that doesn't work for theta equals 0 or theta equals pi. Technically speaking, this identity is only true when both sides are defined. There will be some points where this expression is undefined, but this expression is defined. Because this expression is defined for theta equals 0 and theta equals pi, but this expression is not defined for theta equals 0 and theta equals pi. We don't generally worry about that kind of thing because it turns out that for most purposes, all we care about is the fact that these two things are equal to each other whenever they're defined, and they will both always be defined mostly at the same points. Like there might be a few points where one side is defined and the other isn't, but it's only going to be a few points scattered along the number line. It's not like we're going to have whole intervals or anything where this identity fails. So just keep in mind that when you're doing this, I mean, this is kind of good news for you, right? It makes things easy. You can ignore the question of, oh, did I accidentally change the domain of definition? But keep in the back of your mind that maybe there's some application someday where the domain of definition is going to matter, and then you do have to worry about it, okay? So that's the main thing I want to say, is just be careful about that sort of thing. Again, it's a technical issue that you can mostly ignore, but I do want to point it out. Okay, so we've seen a couple of examples of simplifying these trig expressions. Now, like I said, why would you want to do this? Well, the reason is because something like this, big and ugly and hard to understand what's going on, something like this, secant theta, fairly simple to understand what's going on, at least compared to the original expression. You might not really say, secant theta. Okay, that's still kind of annoying to understand what's going on, but it's not nearly as bad as this thing. It also turns out, for those of you who are going to go on to calculus, that in calculus, you use trig functions for all sorts of stuff, and you really want to get things to be the simplest possible trig functions you can in those cases. Now, in addition to just simplifying expressions, there's another type of problem that we can consider, which really involves a lot of simplifying, but it is a little bit different. And this is establishing new identities for the trig functions. So the idea here is we can prove new relationships that have to hold between the different trig functions by using these ideas. And I think the easiest way to kind of explain exactly what this means is to show you guys an example. So let's pull up a convenient example here. Let's suppose that I want to prove or establish that, let's start off with this one because it's a little similar to one of the ones that we just did, and hopefully that will help with seeing what we're doing. So let's prove that secant theta times sine theta is equal to tangent theta. Now, the general rule for doing these, the general approach, because there is no one fixed thing you're always going to do, but the general approach to these kinds of problems is simplify both sides separately and get them to the same thing. Okay, so we're going to, you don't want to just assume that this is true and start messing with it, okay? You can't just assume what you're trying to establish. So you really have to say, okay, let's see if we can simplify secant theta times sine theta and simplify tangent theta, and eventually in the process of simplifying both sides, we want to see that, oh, they actually simplify to the same thing. Now, a trick for doing this, often, not 100% of the time, but often, you can just leave one side alone. In this case, tangent theta is already reasonably simple. So let's ignore this right-hand side for the moment, and let's try doing this by simplifying the left-hand side, which I'm just going to abbreviate as LHS. You can write it out if you want to. As you know, I like to be lazy about writing things out and use abbreviations when I can do that. So let's try simplifying the left-hand side here and see if we can get that to look something like tangent theta, or at least into a nice simple form where it might be easy to see that this comes out to be tangent theta. So if I think about this left-hand side, I have secant theta times sine theta. Now, a few different things I can do here, but probably the thing that I like to do is to rewrite this in terms of sines and cosines. So, what is secant theta in terms of sines and cosines? Give you a second to think about that. So remember, the cos flip, which means that this is actually 1 over cosine theta times sine theta. Well, that is equal to sine theta divided by cosine theta, but by definition, that is just equal to tangent theta. So we have actually established that this left-hand side simplifies to a form that is identical to the right-hand side. When you have established an identity like this, there are a couple of different ways that you can indicate that you are done with your demonstration. You can write QED. This is from Latin quod erat demonstratum, and it means that which was to be proved, or that which was to be demonstrated. You can also, if you prefer, and I generally do, you can put a little square. The little square is just mathematical notation that means, essentially, we finished demonstrating what it was we were trying to demonstrate. It means the same thing as QED. Maybe if you took a high school geometry class, you learned using QED to end your proofs and things. This is kind of the same idea. So again, to reiterate the method that we used, we looked at this thing and we said, okay, the left-hand side looks more complicated. We're going to start with the left-hand side and we're going to start simplifying it and hope that we get something that looks like the right-hand side. We went along And we did. So we're done. All right, let's take a look at some additional examples of this stuff because I want to demonstrate kind of more of this technique. But if you want to take a little break here, get up and stretch for a minute, go ahead and pause the video here and take a break, clear your head, and come back and look at these examples later. All right, so let us take a look at some additional examples here. So let's suppose that I want to show that tangent of u times cotangent u minus cosine squared u is going to be equal to sine squared u. Okay, I'm going to, when I take a look at proving this, the right-hand side looks reasonably simple, so we're going to leave that side alone for the moment, and we're going to attack this left-hand side and see what we can do to simplify it. So, let's rewrite everything in terms of sines and cosines. I think that will kind of help to see what exactly is going on here. Tangent is, of course, well, let me rewrite this. So we have tangent u, cotangent u minus cosine squared u. Tangent u is sine u over cosine u. So we have sine u over cosine u. Cotangent is cosine over sine. Okay, so we have sine u over cosine u times cosine u over sine u. And then we have minus cosine squared u. Now, the nice thing here is that these cross-cancel with each other. So we end up with 1 minus cosine squared u. Now, we need to go back and think about the Pythagorean identity for a moment. So one of the things that we know about the Pythagorean identity is that the Pythagorean identity tells me that sine squared u plus cosine squared u is equal to 1. But that actually means that sine squared u is 1 minus cosine squared u. So when I see this 1 minus cosine squared u, I can replace this with sine squared u. But now, I started with the left-hand side. I neglected to write that down, which wasn't the best. I mean, you don't have to write down which side you're doing, but it is helpful to say, okay, we're going to work with the left-hand side here and see what we get. And we ended up simplifying the left-hand side until we got down to the right-hand side. Now, when you make a change like this, it can be good, although, again, you don't have to say that you're doing this using, in this case, the Pythagorean identity, just to demonstrate what's going on. Okay, so I started with the left-hand side, and I ended up with the right-hand side, but that establishes this original equality, okay? So this original equation has now been established. Now, make sure that you understand all the steps that went on here. If you feel like any of these were confusing, go back and rewatch and make sure that you can kind of follow along and work this out yourselves. Because, again, mathematics is not a spectator sport. You really need to be able to do all of this stuff in detail by yourself. All right, more examples. What would be another good example to do? So let's suppose that I wanted to establish that here's a pretty good one. Let's suppose that I want to establish that secant to the fourth theta, where'd it go? I've lost it, minus secant squared theta is equal to tangent to the fourth theta minus, or not minus, I'm sorry, plus tangent squared theta. This is a much more complicated example than the ones that we had before. Now, there are a few different ways of attacking this problem, and I'm going to try to show you all of them eventually. But I want to show you kind of the first method. So this is one that actually Professor Mihai, the chair of our department, and I, when I talked to her about this problem last year, because she happened to see me working this problem with the students. So she and I, the interesting thing was, she and I had different approaches for how we would naturally think about this problem. Both are correct, and both of us understand the other approach. We could both do either approach, okay? Anyone could do either approach. But the point is that some people think about these things in a slightly different way, kind of naturally, than the way that other people think about it. And that's okay. I want you guys to do whatever works for you. As long as your arguments are correct, that is what matters. So, method one. And we're going to hope that we can fit all of this into the board in a nice way. So the method one is going to be to use sines and cosines. We're going to rewrite everything in terms of sines and cosines, and we're going to go from there. So if we were to do that, then this is going to, the left-hand side turns into 1 over cosine to the fourth theta minus 1 over cosine squared theta. Because remember that the reciprocal of secant is the reciprocal of cosine. I guess that's probably the simplest way of saying it. Now, if I wanted to take a common denominator here, I would need to multiply this right-hand fraction by cosine squared over cosine squared theta. So this is going to become 1 over cosine to the fourth theta minus cosine squared theta divided by cosine to the fourth theta. This is going to become 1 minus cosine squared theta divided by cosine to the fourth theta. Sorry, that looks like cosine 4 theta. Let's try to make sure that our exponents are clearly exponents. And I can use the Pythagorean identity to say that 1 minus cosine squared theta is actually sine squared theta. So this becomes sine squared theta divided by cosine to the fourth theta. And that is going to be the same thing as tangent squared theta secant squared theta. Although we may end up just caring about this form instead. Okay, now the thing is, I don't know that I can get much further with this particular form. So I'm going to start attacking the right-hand side now and see what I get. If I start with the right-hand side here, tangent to the fourth theta plus tangent squared theta, well, this is going to become sine to the fourth theta divided by cosine to the fourth theta plus sine squared theta over cosine squared theta. Again, I've just rewritten tangent in terms of sines and cosines. So this is now going to become, I need to multiply the right-hand side by cosine squared theta over cosine squared theta. So this becomes sine to the fourth theta divided by cosine to the fourth theta plus sine squared theta cosine squared theta, all divided by cosine to the fourth theta. This becomes sine to the fourth theta plus sine squared theta cosine squared theta, all divided by cosine to the fourth theta. And now, magical things are about to happen for us. I know that this looks like an awful mess, but it turns out to be pretty good. I can factor a sine squared theta out of here. So this becomes sine squared theta times sine squared theta plus cosine squared theta, all divided by cosine to the fourth theta. And now, by the Pythagorean identity, sine squared theta plus cosine squared theta is equal to 1. So this becomes sine squared theta divided by cosine to the 4th theta. But now I claim that I am done because the left-hand side also simplified to sine squared theta over cosine to the 4th theta. So it turned out that, yeah, rewriting this in terms of tangents and secants wasn't entirely necessary. So let's just kind of run over everything we did in this example because, again, it is a complicated example. We started off by looking at this, and in this case, neither side was particularly simple to start with. So I thought, hey, maybe I should just work both sides eventually. So I started off by working the left-hand side. And as I worked through the left-hand side, eventually I got down to sine squared theta over cosine to the 4th theta. I also wrote that in terms of tangents and secants, just in case that turns out to be useful for me later. And then this looked to be about as simple as things were going to get. So then I started working on the right-hand side. And as I worked through the right-hand side, rewriting everything in terms of sines and cosines, I eventually got down to sine squared theta over cosine to the 4th theta, which is the same thing I got on the left-hand side. That means the left-hand side here and the right-hand side here both simplify to the same expression, and that means that they actually have to be equal. Okay, that was a kind of a crazy problem. Now, this is the first method, using sines and cosines. There is a second method that you can use. I want to show you method number 2 here. The second method is to leave everything in terms of secants and tangents. In some ways, this is going to be a little bit shorter. And not involve as many fractions. The complication that we're going to get in this way, because there's always a trade-off. Usually there is a trade-off between the different methods. The trade-off in this case is going to be that we have to deal with secants and tangents instead of getting to just deal with sines and cosines. So method number 2, if I start on the left-hand side, I can take the left-hand side and I can factor out a secant squared. So I would get secant squared theta times secant squared theta minus 1 from the left-hand side. Okay, so now what can I do? Well, it turns out that this is actually a Pythagorean identity kind of thing. How do we get that this is a Pythagorean identity kind of thing? Well, remember that 1 plus tangent squared theta is equal to secant squared theta. That means that tangent squared theta is equal to secant squared theta minus 1. Okay, so that is just the Pythagorean identity rewritten a little bit. So this left-hand side is actually going to become, how do I want to write this anyway? I guess I'm actually going to rewrite both of these things. So I'm going to replace this secant squared theta with 1 plus tangent squared. And I'm going to replace this secant squared theta minus 1 with tangent squared. Okay, that was a little bit complicated, so let's make sure that we understand what happened. This secant squared theta becomes 1 plus tangent squared theta because of this Pythagorean identity. Secant squared theta minus 1, this whole expression comes down here to become tangent squared theta, again, by the Pythagorean identity. So we've double Pythagorean identitied this thing. But now, let's distribute this. This is going to become tangent squared theta plus tangent to the 4th theta, which is, of course, just tangent to the 4th theta plus tangent squared theta, and that's actually just what we have on the right-hand side, and we are done. Okay, so advantages and disadvantages to the two different methods. Well, one of the advantages to this second method is that it's quite a bit shorter and we didn't have to deal with big fractions, okay? When we dealt with sines and cosines, we had to deal with everything in terms of some fairly nasty looking fractions, right? They had things like cosine squared and cosine to the fourth in the denominator. Bit of a mess. The disadvantage is that we have to use a more complicated form of the Pythagorean identity. And if you think about it, the reason that this works and gets rid of the fractions is because all of that stuff involving the fractions is hidden inside of this form of the Pythagorean identity, because this really involves cosines in the denominator. It's just they're hidden because everything is written in terms of tangent and secant. Okay, so which method is better? There is no better method. It's whichever method you like, okay? And you should understand how to do both. But when you are approaching these problems on your own, I think that what you will find is once you get used to doing these, you'll probably find that there is one method that's sort of more natural for you personally to think about. And I want you guys to always remember it's best to do what comes naturally to you first. Now, you want to eventually be able to do it either way, but it's always good to kind of think about what is the thing that is easiest for me to do on this problem. That's what you want to try to do. By the way, if you're curious, I don't even remember whether Professor Mihai said method 1 was how she would think about it, or if she said method 2. I do remember when we talked about it, we had opposite ways that were natural for us to approach it. But the truth is, I think method 2 is the way that I did naturally, and method 1 was the way she did it. I don't actually remember. I could have that backwards. I just remember that I was showing it in class, and then afterwards we talked about it, and we flip-flopped it. We said, oh yeah, we would both have, naturally, if we were just doing this problem, we would have used the opposite methods. But the point is, it doesn't matter. They're both perfectly fine. Now, I want you guys, as a little bit of practice here, in your books, on page 641, this was problem 37. I want you guys to take a look at problem 38. Problem 38 is almost identical to this one, except it's in terms of cosecants and cotangents. So as a little exercise, I would like you guys to, you're not going to turn this in or anything, but as an exercise, go ahead and try to do problem 38 and follow along and see if you can do it first by turning everything into cosines and sines, and then by leaving everything as cosecants and cotangents and doing something like this method 2. The two proofs are going to be almost identical, okay, because they both rely on very similar things, except one is in terms of secants and tangents. You're going to be doing yours in terms of cosecants and cotangents. So again, problem 38 on 641. I don't remember if I put that in your homework for this section or not, but practice it on your own. And if you have any questions, if you get confused as you're going through this, please let me know. Come to my office, talk to me about it, send me an email, and I will help you guys work through it. But I want to leave you guys with that as a challenge to make sure that you really understand what's going on here. All right, I will talk to you guys soon.